Bandwidth is defined as the maximum frequency at which the output of a system will track the input sinusoid in a satisfactory manner. By convention, bandwidth occurs at a gain factor of 0.707, or 1 over square root of 2, or minus 3 dB times the input. So what does this mean? Well, as we saw in class, if you're driving down the road in your car and you take the steering wheel, here's your car, it's not a very nice car, you're driving down the road and you have the steering wheel and you shake the steering wheel back and forth. We know that if you shake that relatively slowly, the car will essentially follow some desired path like that. If you shake it fast, the car will go relatively straight, but it'll kind of just shake around back and forth and back and forth. And this is essentially what the bandwidth is. The lower frequencies, the car can track the input or the movement of the steering wheel, and at higher frequency, it can track in the sense of it goes back and forth, but what you're trying to do is drive it in a larger amplitude. So this would be outside the bandwidth of that car. Another way to think about bandwidth is with respect to inputs given by a person, and let's use the example of a pilot. Let's say a pilot is flying along and gives commands to the stick that look something like this, and this is just notional set of commands. But notice that if we were to try to approximate this signal, this input signal, so this is input versus time, if we were to try to approximate this signal with a Fourier transform, then at each one of these square inputs, we know that we would get some very large overshoot and then so on and so forth. And we would need a lot of frequency content in the Fourier transform at high frequencies. And these high frequencies correspond to places where the plane can't respond. In other words, I can't drive the plane, say, in pitch at those high frequencies, because that would mean that, so if here's your plane, and I've got a wing here, nice, and I'm looking at the pitch angle, then I can't make the pitch angle go up and down very fast. It takes a certain amount of time for the plane to pitch around due to its static stability margin, as well as its inertia and all of the other forces acting on it. So if the pilot were trying to do this, it might be beyond the bandwidth of the aircraft, and the aircraft, instead of following these nice commands, might instead kind of lag behind and overshoot, and then lag behind, right? And so notice we're not tracking the input very well, and that would be beyond the bandwidth of the system. We can look at the idea of bandwidth by looking at a fairly simple example in Simulink. Notice here I have a transfer function, 1 over s squared plus s plus 1, and I'm going to drive it with a sine wave, which has a frequency of 1 radian per second and amplitude 1. And then I can look at the input and the output of these two systems. Notice the input is just a simple sine wave, and the output, while eventually it gets to a magnitude of about 1, it doesn't get there initially, so it has a little bit of delay in how quickly it responds. And notice it doesn't get to full magnitude right away. And this delay plus the increasing magnitude causes a slight phase difference between the two. Notice this one peaks around a little before 2 and out at 8. This one peaks at about 3 and then at about 9 and then 16 and so on. So this output is lagging behind the input. If I go ahead, and that's the phase difference. If I go, and then the bandwidth here, notice the difference between the two in terms of magnitude is pretty close. They're both about 1. If I increase the frequency to, say, 10 radians per second, and now we run this, now it gets a little messy numerically, but this is just a sine wave, back and forth and back and forth. And if I can make this, I can clean this up by going into the configuration parameters and setting my tolerance a bit higher. And now if I run this, I'll get a better looking sine wave. So there's my sine wave, and that's the input. And notice on the output, I get this weird transient, but then in the steady state, I get a sine wave, but notice its amplitude is only 0.1, so it's about 1% of the magnitude of the input. So it's been reduced significantly in magnitude. And if we were to look at the phase shift, which is a little hard to see here, we would see that there's also a lot of phase shift. I can verify this all by using the Bode plot. So if I define a transfer function as 1 and 1, 1, 1, and then type Bode L, and we go ahead and let me put the grid on for that figure. And let me make this larger. We can see, indeed, that at 1 radian per second, in fact, there is 0 dB for this particular system. So it would transmit a sinusoid with no change in the magnitude. But notice there's a 90-degree offset in the phase, and we saw that. Out at 10 radians per second, then there's a decrease in the magnitude of minus 40 dB, which is about right when you compare 10 to the 1% times, you get, that's 2 orders of magnitude log 2. So then that gives you times 20, gives you 40, minus 40 dB. And notice there's a fairly large phase difference between the two. So the gain margin here would be when you have minus 3 dB, which so the bandwidth of the system would happen at minus 3 dB, which would happen somewhere around here, a little after 1 radian per second, maybe 1.5 radians per second.